In Chapter 7, we're going to talk about internal forces. So, as an example, let's start out here with a cantilevered beam. So it's fully supported here at the left. And let's apply some loads. So I'll apply an angled load here, P, maybe another load here, P vertical. And now I want to analyze the internal forces. So I'm just going to arbitrarily make a cut in my beam here, section AA, cut this, and I'm going to do free body diagrams. So here we go. Let's set up some free body diagrams. So first, I'll have everything to the left. And what we end up here with is our reactions. So we'll have a force in the x direction, AX. We'll have force in the y direction, AY, and a moment about A. So let's call this A, this B, and our section is C here. Or we can call this B, because we don't need a C really. So I moved it down a little, make some room. So now if we look over here on the cut side at B, the cut at section AA, we have a force, which we're going to call a shear force in the y direction. We have a force normal, and we also have a moment here to counteract the other moment. Now, of course, some of these are not drawn in the correct direction, but I drew these this way because I want to represent those in the positive sense. And we'll talk about that in a second. And of course, I can draw this other side of the cut over here, the rest of the beam. We'll have the loading on it in this one, in this portion. Then we'll have opposing forces. So there's an NB. We'll have the shear force. And we'll have a moment. Equal and opposed. So we'll call the moment the bending moment. We'll call this normal force or axial force, and then we have the shear force down at the bottom. So I drew those in a certain way on these internal forces a certain way, and the direction I drew these is going to conform to what we consider positive direction, and it's just an arbitrary decision what that is. So just to talk about it here, for our positive convention, for our axial load, it's always going to be pointed like this away from the section, and that essentially will put our section in tension. If you think of it like this, then tension is our positive sense here. Then we have the shear, what we want to call positive shear. And again, this is just arbitrary. Could it be defined the other way, but we're just not going to. So when it's down on the right side or up on the left side, this is positive shear. These are the normal force. Positive shear. And Then finally, let's do our positive moment and our positive moment curves this way and this way. So positive moment produces a bending of the beam that makes it smile. So you can use that to help you remember. You're just going to have to memorize that positive shear is down on the right of the section and up on the left of the section. Axial or tensile load as positive for the normal is pretty easy to remember. So now let's look at a example, demonstrate some of these ideas. And so for the beam loaded as such over here, where this maxes out on the left at 20 or 1200 newtons per meter, let's cut this at C and look at the internal loads. So if I were to make that cut at C here, see if we can shrink this just a little bit so it matches up better with the picture above. So if we make this cut at C, we see that, okay, let's sketch in our internal loads. So we have normal force, we have a shear force, and I'm drawing these in the positive sense here, but they could be drawn incorrectly. But we'll find out. So that's our internal loading at the cut. Then I have my external loading, which is this triangular shaped non-uniform load. And of course, if this is 1200 here, and this is a linear line going down, and this C is at the halfway point, let's put some dimensions here of 1.5 and 1.5. These are in meters. Then C is at the halfway point. Well, this obviously is 600 newtons per meter. Let me make it red so it matches up with the dot. 600 newtons per meter. So that's the value up here at this peak. So I can replace this with a concentrated load at a third the distance from the left edge, as we found with triangles, which is equal to this area of this triangle, the little triangle here, which is, so I'll call this P equals, so it's 1/2 600 times the width of 1.5, and that's going to be 1/2 of 600 is 300 times 1.5 is 450. 450 newtons. Concentrated force. And that's my free body diagram. So let's just do some fundamental analysis here to figure some things out. First, we'll sum forces in the x direction equal to 0, and we see that we have n. It's actually minus. Let's make this sense positive. So therefore, n equals 0. That is our first solution, our first load. And let's sum forces in the y, set them equal to 0. Let's call this direction positive, as you might imagine. So we have, so this is v. So we have v minus p, which is the same thing as v minus 450 newtons. So therefore, V just equals 450 newtons. And finally, let's sum moments about the cut. And as usual, we'll call this our positive direction. So don't confuse positive directions here for my equations of equilibrium. Oops, we crashed. So as I was saying, don't assume the positive directions for my equations of equilibrium with the positive sense for my loading on the cut section, my internal loading. So if we sum moments about the cut, we're going to have minus m, because that's rotating counterclockwise, and then we also have minus p times the moment arm here, and we said that was 1/3 the distance, which will be 0.5 meters. So p times 0.5, and we saw that p was equal to 450. So m then is going to equal 450 times 0.5 is 225. So m is going to equal, pull our m over here, minus 225 Newton meter. And that's it. So we've calculated the internal forces at the cut on our beam. Okay, so we can describe the variation of our shear and our moment along the length of the beam using this approach now. Since we can figure this out at any point, we can do this as a function of x. And that's what we'll set up here and do. So first, let me figure out. So I have this beam here that is simply supported. And the first thing I want to do is let's figure out the reactions on this beam. So here's our beam. Now we have a triangular distributed load here, so that's going to be, I'm going to replace that with just, for my analysis purposes, with a concentrated force. 6 times 9 is 54 divided by 2, so this is P equals 6 times 9. Half of that, because that's the area of this triangle, equals 27 kilonewtons. And if this distance is then 6, this distance is 3, then we can sum moments about, let's call this A, sum moments about A and B, and find our reactions. You're going to find that the reaction here is 9, and the reaction here is 18. And the sum of those two is 27. So that's where we're going to start. And I think I'll finish up here, and we'll work on this in the next video.